So looking a little deeper in how to evaluate features and subsets of features. So there are basically three types of methods. The first one are filter methods. They explore the general characteristics of data and that is the positive one, they are independent of the learning algorithm. So they generally work as a pre-processing step, typically. So filter methods are pre-processing steps, pre-processing filters. And even if you don't know exactly what kind of learning algorithm you employ later on, you can use them because they are somehow independent. Yeah? The second class are so-called wrapper methods. So in that case is exactly this one here. So you use the learning algorithm to evaluate the subspace. So you somehow still use the feature selection as a pre-processing step, but now you evaluate all the features or the subspaces you came up by employing your learning algorithm and then evaluate it. Yeah, and then if you are happy with the evaluation, you keep it. If not, you look for a different subspace with a certain feature subset generation. And then, so those methods are obviously dependent on the learning algorithm. Yeah? And the third one also depends on the learning algorithm and only works with those that allow that, because they are called embedded methods, because you embed the feature selection into the learning algorithm. So a very good example is, again, the decision trees. Decision trees have a feature selection as part of the learning algorithm, because at each split you do a kind of feature selection. You select the best feature for splitting and then you do the split. Yeah? So those methods are called embedding methods or embedded methods here. Yeah, even closer look to all those three things here. So filter methods, the basic idea is to assign a kind of importance score or significance score to each feature in order to filter out the useless ones. Yeah? So you typically look at each feature individually and then get rid of the less significant ones. Yeah? And example methods we will take a closer look here are information gain, chi-square statistics. You can use even TF-IDF for text, for example. So you can also so those things here, information gain and chi-square statistics, are very general measures. But as you can see here, you can even come up with some application-specific features like or important scores like TF-IDF, for example. The most important feature is that of those methods is that they are disconnected from the learning algorithm. As I told you before, you can even do that as a general feature pre-processing step, regardless what you employ later. And very often, for example, if you are in the feature in any scenario, if you don't know anything too much about your data, even in the supervised scenario, you typically want to employ different algorithms later on and come up with the best one. So those methods are good in those scenarios because they are they work with any learning algorithm you want to employ later on. The pro, it's fast, it's generic, as I told you before, and it's even typically simple to apply and simple to implement, but very often implementations in Python or whatever exist. On the downside, it doesn't take into account interactions between features. We will see that when we have a look at those measures here, because you really just evaluate each feature by its own, individually, and then so it somehow assumes that the features are not correlated, are independent to each other. Yeah? So it will lose in the case where you have individual irrelevant features that form together relevant ones, subspaces. Yeah? So in this scenario where you have irrelevant features that together form relevant subspaces, those methods will fail. Yeah? And the question, of course, also is are those methods here, are those evaluation measures here probably too generic for your application? Of course, you can come up with application-specific ones, but maybe also too generic for your learning algorithms you want to employ later on. Yeah, next are the wrapper methods. Closer look to wrapper methods. So, yeah, in that case, as I told you before, a learning algorithm is employed on the subspace you want to evaluate, and the performance of this learning algorithm is used to determine the quality of the selected features of this subspace in that case. The positive side first, it takes feature dependencies now into account, because you don't look at individual features, but you always look on the complete subspace you right now have as a candidate, and do the performance measure in the complete subspace, not on the individual features. So interactions between feature subsets can be employed here, and you have because you have an interaction between the search for features and the model selection actually. The downside is, of course, you have a higher risk of overfitting than filter techniques. Filter techniques are more generic; those are very specific. Yeah, and also the computational cost can be quite high, especially if the classifier, the model selection and the model fitting here has high computational costs. In that case, of course, the whole thing can be quite computational costly. Third one, embedded methods. They try to somehow have a compromise of both methods before. So they try to integrate the feature selection into model building. As I told you before, the best example is the decision tree induction algorithm. At each split, at each node, there is a kind of feature selection. The pro is it's less computational intensive than the wrapper methods, but on the downside, it's specific to a learning method. So we have, you know that decision trees have a high tendency of overfitting, and that's exactly the point that is mentioned here. You have a high tendency of overfitting here. Good. For the search strategies in the feature space, so this is the second question, originally the first question, now the second question we take care of. There's very different methods, basically approximation algorithms for this huge search space of 2 to the power of n possible solutions. So there are typically the so-called forward selection methods. They start with an empty feature space and just try to add one by one irrelevant features until you reach a given target dimensionality typically. Backward selection is the other way around. You start with all features, so with a whole feature space, and try to remove irrelevant features until again you reach a target dimensionality typically. And then, so obviously those two things are, this one here has again the problem that you evaluate features individually in both cases actually. So the other ones try to somehow account for those effects that you may see some patterns in a specific subspace, but if you add or remove features, the patterns are gone. Yeah. So those two methods, forward and backward selections methods, will not have a chance to capture those things. So those other methods try to capture those things. So you have branch and bound things like a priori or FP growth in the frequent item set mining thing, if you have a monotonic evaluation method. Only in that case, of course, that works. Yeah. And sometimes you just go for Monte Carlo. So Monte Carlo is a nice term for just random. Yeah. So randomized search for k-dimensional projections. That could be also a kind of idea to employ, and there are a lot of methods that propose to just randomize the search for your target dimensional subspace.